calculate voltage drop for 12 volts pole light circuit, several steps are involved. First, determine the voltage drop percentage, or VD%. This is calculated using the formula VD% equals distance times current times resistance, all divided by voltage times 100. The distance in this case is 85 feet. The current is calculated by dividing the power, 300 watts, by the voltage, 12 volts, which equals 25 amps. The resistance depends on the wire size and material. We'll be using THHN copper wire, and resistance values will be provided for various American wire gauge, or AUG, sizes. Second, determine the actual voltage drop, or VD. This is calculated using the formula VD equals VD% times voltage divided by 100. Third, select the appropriate wire size. Calculate the maximum acceptable voltage drop, or VD maximum, based on the required voltage drop percentage. VD maximum should be less than the VD calculated previously. VD maximum equals VD% times voltage. Use a table providing resistance values for different THHN wire sizes to find a suitable size that meets the VD maximum requirement. Here is an example. Assuming a voltage drop percentage of 2% is acceptable. Calculate VD maximum. VD maximum equals 2% times 12 volts, which equals 0.24 volts. Now calculate VD for different wire sizes using the formula VD equals VD% times voltage divided by 100. For 12 AWG, VD equals 2% times 12 volts divided by 100, which equals 0.24 volts. This meets the requirement. For 10 AWG, VD equals 2% times 12 volts divided by 100, which equals 0.16 volts. This also meets the requirement. For 8 AWG, VD equals 2% times 12 volts divided by 100, which equals 0.8 volts. This exceeds the requirement, meaning it's a better performing but possibly more expensive option. For 6 AWG, VD equals 2% times 12 volts divided by 100, which equals 0.4 volts, also exceeding the requirement. And for 4 AWG, VD equals 2% times 12 volts divided by 100, which equals 0.2 volts, also exceeding the requirement. Therefore, based on an acceptable voltage drop percentage of 2%, either 12 AWG or 10 AWG THHN wire can be used. Now let us look at the numbers. Let us calculate the voltage drop and wire size needed, using the formulas provided. Firstly, calculating the voltage drop percentage. VD% equals distance times current times resistance slash voltage times 100. Secondly, to calculate the actual voltage drop, use the following formula. VD equals VD% times voltage slash 100. Thirdly, to select wire size, the maximum voltage drop acceptable must be calculated. VD max equals VD% times voltage. Now let us determine some wire sizes that meets the VD max requirement. We will need the following wire sizes: wire size THHN and the resistance in ohms per foot. For 12 AWG the resistance is 0.16 ohms per foot. For 10 AWG the resistance is 0.1 ohms per foot. For 8 AWG the resistance is 0.63 ohms per foot. For 6 AWG the resistance is 0.4 ohms per foot. For 4 AWG the resistance is 0.25 ohms per foot. These values for resistance are needed for calculating voltage drop. Now, let us assume we will use a 2% voltage drop as acceptable. We will now calculate VD max. VD max equals 2% times 12 volts equals 0.24 volts. Now let us calculate the voltage drop for different wire sizes. Firstly, for 12 AWG VD equals 2% times 12 volts slash 100 equals 0.24 volts, which meets the requirement of 0.24 volts. Secondly, for 10 AWG VD equals 2% times 12 volts slash 100 equals 0.16 volts, which also meets the requirement. Thirdly, for 8 AWG VD equals 2% times 12 volts slash 100 equals 0.8 volts, which is better than the requirement. Fourthly, for 6 AWG VD equals 2% times 12 volts slash 100 equals 0.4 volts, which exceeds the requirement. Lastly, for 4 AWG VD equals 2% times 12 volts slash 100 equals 0.2 volts, which exceeds the requirement as well. Based on these calculations, either 12 AWG or 10 AWG THHN wire can be used and meet the requirements. Selecting a wire size that results in less voltage drop can improve the efficiency and performance of the pool light. Remember to always consult local electrical codes and regulations and consult with a qualified electrician to ensure safe and compliant installation. When performing electrical calculations, it's essential to consider various factors to ensure the safety and efficiency of the electrical system. Let's explore some additional aspects to keep in mind during the voltage drop calculation and wire size selection process. Firstly, ambient temperature. The ambient temperature around the wire can affect its resistance. Higher temperatures increase resistance, leading to higher voltage drop. THHN wire is rated for a specific maximum operating temperature, so ensure the chosen wire size is appropriate for the expected ambient temperature. Temperature correction factors may need to be applied based on the National Electrical Code or NEC tables. Secondly, conduit fill. If the wires are installed in a conduit, the number of conductors in the conduit affects the allowable ampacity of the wires. High conduit fill reduces the heat dissipation capability of the wires, requiring a dirting of the ampacity. Consult NEC tables to determine the appropriate dirting factors based on the number of conductors in the conduit. Thirdly, terminal temperature rating. Electrical equipment, such as transformers and pool lights, have terminal temperature ratings. The wire connected to these terminals must have a temperature rating equal to or higher than the equipment's terminal temperature rating. Typically, equipment is rated for 60 degrees Celsius or 75 degrees Celsius. Ensure the THHN wire selected is rated for the appropriate temperature. Fourthly, voltage drop limits. While a 2% voltage drop was used in the example, the NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. For sensitive electronic equipment, even low voltage drop limits may be necessary. Consider the specific requirements of the pool light and any other connected equipment when determining the acceptable voltage drop percentage. Fifthly, conductor material. The calculations assumed copper conductors. If aluminum conductors are used, the resistance per foot will be different. Aluminum has a higher resistance than copper, so a larger wire size will be needed to achieve the same voltage drop. Ensure to use the appropriate resistance values for the conductor material being used. Sixthly, future expansion. Consider any future expansion or additional loads that may be added to the circuit. Selecting a wire size that can accommodate future loads will prevent the need for costly upgrades later on. It's always better to oversize the wire slightly to account for potential future needs. Seventhly, physical protection. Ensure the wire is adequately protected from physical damage. If the wire is exposed to potential damage, such as in an underground installation, consider using a conduit or other protective measures. Direct burial rated THHN wire is also available for underground installations. Eighthly, local codes and regulations. Always comply with local electrical codes and regulations. These codes may have specific requirements for wire size, installation methods, and safety measures. Consult with a qualified electrician or electrical inspector to ensure compliance. Ninthly, safety. Safety should always be the top priority when working with electricity. Always disconnect power before working on any electrical circuit. Use appropriate personal protective equipment, or PPE, such as insulated gloves and safety glasses. If unsure about any aspect of the electrical work, consult with a qualified electrician. Let's consider an alternate approach to calculating voltage drop, which involves using a voltage drop calculator. Voltage drop calculators are available online and can simplify the calculation process. These calculators typically require inputting the voltage, current, distance, wire size, and conductor material. The calculator then provides the voltage drop percentage and the actual voltage drop. These calculators can be a useful tool for quickly determining the appropriate wire size for a given application. However, it's important to understand the underlying calculations and principles to ensure the calculator is being used correctly. Also, voltage drop calculations are based on certain assumptions, such as a constant load and a uniform distribution of current. In reality, these assumptions may not always hold true. Therefore, it's important to consider the specific characteristics of the electrical system when interpreting the results of voltage drop calculations. Here are some additional factors to consider when selecting wire size. Firstly, directing factors. As mentioned earlier, directing factors may need to be applied based on the number of conductors in a conduit, the ambient temperature, and other conditions. These directing factors reduce the allowable ampacity of the wire, which means a larger wire size may be needed to carry the same amount of current. Secondly, correction factors. Correction factors may also need to be applied based on the ambient temperature. These correction factors adjust the resistance of the wire based on the temperature. Higher temperatures increase resistance, which means a larger wire size may be needed to achieve the same voltage drop. Thirdly, conduit size. The size of the conduit must be large enough to accommodate the wires being installed. The NEC specifies the maximum number of conductors that can be installed in a given size of conduit. Ensure the conduit size is adequate for the wire size being used. Fourthly, pull boxes. For long wire runs, pull boxes may be needed to facilitate the pulling of the wires through the conduit. Pull boxes provide access points for pulling the wires and can reduce the pulling tension on the wires. Fifthly, wire lubrication. When pulling wires through a conduit, it's important to use a wire lubricant to reduce friction. Wire lubricant makes it easier to pull the wires and can prevent damage to the wires. Sixthly, grounding. Ensure the electrical system is properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to protect against electrical shock. The size of the grounding conductor must be appropriate for the size of the circuit conductors. Seventhly, overcurrent protection. The circuit must be protected by an overcurrent device, such as a circuit breaker or fuse. The size of the overcurrent device must be appropriate for the ampacity of the wire. The overcurrent device protects the wire from overheating and potentially causing a fire. Remember that electrical work can be dangerous, and it's important to take all necessary safety precautions. If unsure about any aspect of the electrical work, consult with a qualified electrician. Now let us do one more review. Firstly, calculate the voltage drop percentage VD%. VD% equals distance times current times resistance slash voltage times 100. Secondly, determine the voltage drop VD. VD equals VD% times voltage slash 100. Thirdly, select wire size. Calculate the maximum voltage drop acceptable VD max based on the required voltage drop percentage VD%. VD max should be less than the VD calculated in step 2. VD max equals VD% times voltage. Now for the values of wire size THHN and resistance ohms per foot. 12 AWG is 0.16. 10 AWG is 0.1. 8 AWG is 0.63. 6 AWG is 0.4. 4 AWG is 0.25. Now we are going to assume a voltage drop percentage VD% of 2% is acceptable. VD max equals 2% times 12 volts equals 0.24 volts. Now calculate VD for different wire sizes using step 2. 12 AWG VD equals 2% times 12 volts slash 100 equals 0.24 volts meets requirement. 10 AWG VD equals 2% times 12 volts slash 100 equals 0.16 volts meets requirement. 8 AWG VD equals 2% times 12 volts slash 100 equals 0.8 volts exceeds requirement. 6 AWG VD equals 2% times 12 volts slash 100 equals 0.4 volts exceeds requirement. 4 AWG VD equals 2% times 12 volts slash 100 equals 0.2 volts exceeds requirement. Therefore, based on the acceptable voltage drop percentage. Either 12 AWG or 10 AWG THHN wire can be used. Another element to consider is the type of load the pool light presents. Pool lights can be incandescent light-emitting diode, or LED, or other types. Each has different characteristics that can affect voltage drop. Incandescent lights draw a consistent amount of current, making calculations straightforward. LED lights, however, may have electronic drivers that can affect the current draw and power factor. Power factor is the ratio of real power, or watts, to apparent power, or volt amps. A low power factor can increase the current draw, leading to higher voltage drop. If the pool light has a low power factor, it may be necessary to use a larger wire size to compensate. The power factor of the pool light should be indicated on the product label or in the specifications. If the power factor is less than 1, it may be necessary to use a power factor correction capacitor to improve the power factor and reduce the current draw. Another factor that can affect voltage drop is the presence of harmonics. Harmonics are distortions in the voltage and current waveforms that can be caused by nonlinear loads, such as electronic pulse and variable frequency drives. Harmonics can increase the current draw and voltage drop, and can also damage electrical equipment. If the pool light is connected to a circuit with significant harmonic distortion, it may be necessary to use a harmonic filter to reduce the harmonics and prevent damage to the equipment. Harmonic filters are typically installed at the source of the harmonics, such as at the electrical panel. Also, consider the grounding system. Proper grounding is essential for safety and can also affect voltage drop. A properly grounded system provides a low impedance path for fault current to flow back to the source, which helps to protect against electrical shock. The grounding conductor should be sized according to the NEC and should be properly connected to the grounding electrode system. Now let's delve deeper into the practical considerations of selecting THHN wire for the pool light application. THHN wire is a popular choice due to its heat resistance, moisture resistance, and flame retardance. It is commonly used for general-purpose wiring in residential, commercial, and industrial applications. However, it's important to ensure the THHN wire is suitable for the specific environment where it will be installed. For example, if the wire will be exposed to direct sunlight, it should be sunlight-resistant THHN wire. Sunlight-resistant THHN wire is designed to withstand the damaging effects of ultraviolet radiation, which can cause the insulation to degrade over time. Also, if the wire will be installed in a wet location, it should be wet location rated THHN wire. Wet location rated THHN wire is designed to withstand moisture and prevent corrosion. It's also important to consider the ampacity of the THHN wire. Ampacity is the maximum amount of current a wire can safely carry without overheating. The ampacity of THHN wire depends on the wire size, the insulation temperature rating, and the ambient temperature. The NEC provides tables that list the ampacity of THHN wire for different conditions. It's important to select a wire size that has an ampacity equal to or greater than the load current. In the example, the load current is 25 amps, so the THHN wire should have an ampacity of at least 25 amps. It's also important to consider the voltage rating of the THHN wire. The voltage rating is the maximum voltage the wire can safely withstand. The voltage rating of THHN wire is typically 600 volts, which is suitable for most 120 volts and 240 volts applications. However, it's important to ensure the voltage rating of the THHN wire is appropriate for the specific application. Furthermore, let's discuss the installation practices for THHN wire. Proper installation is essential for ensuring the safety and reliability of the electrical system. THHN wire should be installed in accordance with the NEC and local electrical codes. It should be properly supported and secured to prevent strain on the wire and terminals. The wire should be protected from physical damage, such as abrasion or impact. If the wire is installed in a conduit, the conduit should be properly sized and installed to prevent damage to the wire. The wire should be properly terminated at the electrical equipment. The terminal should be clean and free of corrosion. The wire should be securely fastened to the terminals to prevent loose connections. Loose connections can cause overheating and potentially lead to a fire. Also, it's important to use the correct tools and equipment when installing THHN wire. Use a wire stripper to remove the insulation from the wire without damaging the conductor. Use a crimping tool to crimp connectors onto the wire. Use a torque wrench to tighten the terminals to the proper torque. Using the correct tools and equipment will help to ensure a safe and reliable installation. Remember, electrical work can be dangerous, and it's important to take all necessary safety precautions. If unsure about any aspect of the electrical work, consult with a qualified electrician. Always follow the manufacturer's instructions for the electrical equipment being installed. The manufacturer's instructions provide important information about the proper installation and operation of the equipment. The instructions may include specific requirements for wire size, overcurrent protection, and grounding. Following the manufacturer's instructions will help to ensure the equipment is installed correctly and operates safely.